So I'm excited to talk today about symbolic regression. And so generally, the relationship uh, with data and trying to model data is one of making a hypothesis, sort of assuming a functional form, and then fitting that form using the data. And there are different mechanisms of fitting it. For example, linear regression, you're assuming a linear relationship of the dependent variable with the independent variables, and then you're trying to come up with the coefficients, and there are methods of doing so, and all these different types of regressions kind of follow that. Um, and then you have some sort of more sort of esoteric, some more sort of black boxy techniques like neural networks or machine learning, which are sort of you don't really have a functional form. I mean, you can uh, if you go to great lengths, you can recover some sort of functional form. It's going to be extremely obscure, but it's more of you really have a lot of parameters in those approaches. So if you have a lot of data, then the parameters still are relatively fewer than the amount of data you have. You can fit those parameters and create a model that's pretty accurate. So you have those types of approaches, um, but we don't really have an approach where if you have the data and you're trying to recover the governing equations, the equations that generated that data from the data itself, without assuming the functional form first, say, I hypothesize that the relationship between the independent variable and the dependent variables can be one of these three forms. And then you check those three forms, you do the work, and you find out that two of those forms don't really work, and the third one works. You know, what if you could skip all that and just have the data tell you what equation generated it? Now that seems sort of magical, and it is because it doesn't really exist. But we do have a technique that can get us sort of an inkling of an answer, in some cases the answer, and that's called symbolic regression. It's pretty exciting. It's and So let me kind of try to explain it through an example from, say, physics, my favorite subject in college. So let's see. So let's say we observe some data. So we have, and we graph it. Okay. So we have some data, we have force, and we're running some experiments. We have two masses, mass, we have mass one and we have mass two. And we're running some experiments. We're measuring sort of the gravitational force between them. So the sort of the force of gravity between them, and we're taking some data points. So if this is force, and then we have distance on the x-axis, so the distance between the two objects, and we're measuring how they're related on sort of on this two-dimensional axis, and we observe some points. These are all data points. So we've painstakingly collected all this data, and so we can kind of sort of infer that the relationship between the force and distance must be um, inversely related, because as the distance increases, the force sort of is decreasing, and it's not decreasing linearly, so it's maybe not a linear relation, but some sort of exponential, or an exponent on the inverse relationship. So we sort of infer that the relationship is inverse with distance if I indicate distance with an r, and then there's some sort of x here because it's not a linear relationship. And then, say, through theory and through additional work, we figured out that it's actually varies by the square of the distance. And then, in order to make the relationship sort of more exact, we have a gravitational constant. And now we have our formula for the gravitational force between bodies, and this is how, in sort of Newtonian mechanics, we can, using this equation, sort of classical mechanics, we can chart the motions of the heavenly bodies, the moon and planets and stuff like that. So that's generally been the path. You observe some data, and then you sort of hypothesize some relationship, and then you use the data to fit uh, that functional form and see if that's true. And this in the laws, in sort of the physical sciences, you generally have some laws that generate sort of clean data, and as experimentation improves, maybe you get pretty tight data, so it follows exactly the functional form. When we are dealing with sort of man-made data, so not really physical sciences, we are dealing with data that's generated off of uh, banking processes or all this human activity that we have. Data can get really, really messy. And so is it possible to infer or extract a mathematical relationship from the data itself, skipping over the steps of a human hypothesizing or bringing our own biases to the equation, to the table? Because generally in predictive modeling and data science, we're taught to you should understand how, say, the individual regressors are related to the dependent variable, and then you're trying to kind of guess at the functional form. But in this case, symbolic regression is pretty exciting. It has a lot of limitations, this process, but I think this is a technique to watch out for the future. And I include this paper as well. That's pretty interesting, where they have actually shown they were able to recover equations of, say, fluid dynamics that took us 30 years to, experts, that took them 30 years to try and figure out what those equations look like. And in this example, they showed that they were able to recover that straight from the data. So that's pretty interesting, pretty remarkable. Okay, so what are we going to be doing in this example, this Python example? So the first thing we do is we load some. I'm not going to go through all the different things. This is extracted from a library called GPLearn. So this whole example is sort of representation of that, and I have the link here. And so let's go through it. So we first load some of our dependencies. So we're loading the GPLearn package called Symbolic Regressors here. And in the next step, we are generating some data. So we know we know how we are generating the data. We generate data using this equation. So y is related to x naught and x1. Okay, so x naught and x1 are our two features or regressors, and it's related as x naught squared minus x1 squared plus x1 minus 1. So we know the exact, so we're cheating in a way that we know the exact equation, and that's how we generate the data. But we are not cheating when it comes to actually applying the method, because we're just going to present the data that we generated to the method, and we're hoping, if things work out, that the method will reveal this equation back to us. Okay, so we're going to be able to recover the equation from the data. All right, so here we're generating the data. So using this sort of numpy function, we're generating the data. X naught is being generated between -1 and 1 in increments of 0.1. And then x1, we're generating sort of random values between those two in those steps. And then we're generating the values of sort of, we're calling y truth. This is our sort of true values of y and how they're related to x naught and x1. And then we're plotting it to see what it looks like. And you'll see this sort of complicated shape, sort of saddle shape. So we have x naught and x1 here, and then y is on the sort of y-axis. And we see this three-dimensional complicated shape. And what we're going to be doing is we're going to be generating data points on this surface, on this complicated surface. So, look like, okay, we have a bunch of data points, and then we're going to present them to the algorithm, hoping to recover this equation back. Okay, so in the next one, we are generating some samples, some training samples and some testing samples. And then in this step, we are running the symbolic regression uh, function or algorithm. And you'll see it's not a lot of code. It's actually quite surprisingly, and that's one of the benefits of using something like Python. I mean, you can do a lot with very little code. So here, what's happening now? It's fitting that it's running the symbolic regression. It's generating a population of possible functions. So what it's doing is it's sort of generating this. If you can think of like 100 different functions, and each of them has some sort of mathematical operators. It's sort of guessing. It's already done. It's run through, but it's guessing that maybe it's related. Maybe the function looks like x naught cube plus x naught x1, or it looks like x naught squared plus x1 squared minus x1, or it looks like this. So it's kind of generating all these possibilities, even longer functions. And then it's then comparing the fitness function. So maybe it's comparing some error metric like r squared. It's measuring, what is the prediction that we get from those functions versus the y truth. So the function that it kind of assumes, maybe it calls it y prediction, and then it's comparing it to y truth, and it's saying, well, is it doing a good job or is it doing a bad job? So in the first example, for example, we have the fitness is 0.32 measure. We want that number to be lower than our stopping criteria, which is 0.01. So 0.32 is pretty high. So we didn't do a very good job in the sort of like the first generation of functions. We have a whole bunch of functions. The average fitness is 458, so extremely high. The best individual function out of that population had a fitness of 0.32. And using that, it's sort of like an evolutionary concept that we use in these things called genetic algorithms, where you generate a whole bunch of random functions. And then out of them, you say, okay, these are the 20 that perform really well. Let's take them to the next generation, and then let's sort of join them with each other, sort of cleave them in different places and join the different segments to each other and try to come up with new functions that are possibly better. So you can kind of see where that evolutionary concept is coming into place. And then you generate subsequent generations hoping that that fitness function kind of goes down. And it does in this case. So it goes down quite a bit. So, it kind of didn't go down in the first couple of generations. In fact, the second generation, we don't really see any change, hardly any change. Then, by the third, fourth, fifth generation, it starts to go down really after the fourth and fifth generations. Sort of the sixth or seventh generation, it's below our stopping criteria. So the function, we have really come upon possibly a really close equivalent to our original function, and we can recover the original, or we can recover what the program is telling us what the function is here in this step. It looks like a strange syntax that this GP-learn program has, but we can make sense of it. So for example, this SUB means that subtract the two functional forms that are within this sub bracket. So this form and then this form we subtract from each other. And even then it looks like this strange equation, this y. And then we can use some algebra to sort of simplify it. And when we're done simplifying, it looks like y equals x naught squared minus x1 squared plus x1 minus 0.999. So if you compare it to the function we know is how the true value of y is generated, it's extremely close, except that we have 0.999 except for the -1. So we have essentially recovered our original function straight from the data. And now we can see how well our function did compared to some other methods like, say, decision tree or random forest. I'm not going to go through, decision tree or random forest in this example. I'll make videos later on that. But we can run that, and then we can compare the performance. So here we have our true data points. Okay, so our true data points are ground truth, and then what does our functional form sort of look like based on our symbolic regressor, so pretty close to the original. So the R squared is essentially 1.0. So we it's very close. And then how does it look like based on decision tree or random forest? So poorer performance using those algorithms. And you can see sort of like the solution space is sort of jagged. And that's a feature of decision tree because it's kind of making those sort of hard distinctions between in the solution space. So you have these hard boundaries, and it looks like some sort of graphic that was rendered in the 80s or something of a video game. So it's very kind of jagged and pixelated. Random Forest does a slightly better job, and there are reasons why, and I'll go through it in a subsequent video. But we can see how sort of this works, and you can play with this example. You can sort of go to say a cube function, so you can now see this kind of different representation and sort of slightly more complicated. If you do change this example, note that you'll have to change the training samples here as well, so to cubed, and then you'll run your symbolic regressor again, and let's see if it runs in a sort of timely manner. It may not, it may fail. So there are when it doesn't really converge at all, so the fitness criteria doesn't really go down to our stopping criteria, say 0.01. It'll kind of hovers around some value, it gets stuck, so it never really is able to recover the original equation. And that's always a possibility. I mean, this method is very expensive. You can see it's kind of slow. There's no guarantee that we will find an answer. If we do find an answer, there's no guarantee that's exactly the right answer. The good thing about symbolic regression is it tries to strike a balance between, the complexity of the equation and the accuracy. So, principles of model parsimony, you want to find a model that's simple. You don't want this complicated model that can approximate any function. You want the simplest possible model. So the symbolic regression algorithm tries to strike that balance. So that's really interesting. And we can see that the fitness function is going down. So hopefully it's getting close to finding the right functional form. Let's see. And I think when you see the code later, I'll add some description along all of these different sort of criteria for the symbolic regressor, so that you can play with them to improve the odds that you find a solution. So we were not able to find a solution that went below our stopping criteria of 0.01. But we can still recover the equation. And I'm not going to do the algebra here, but I think I'll possibly indicate it in the example when I post it as to what that kind of looks like. But let's measure the performance of the different algorithms. So symbolic regressor actually gets very close. So we can see sort of the functional form that it's carving is very close to the original. So once we simplify this using algebra, I think it'll be very close to our original equation. Not exact, but close. Then when we look at decision tree and random forest, they also do a really good job of capturing the general form of the original function. But you can see that they don't do quite as good a job as symbolic regressor. There is another thing, once again, I think I'll mention that there are no guarantees. I mean, you might change this function in somewhat simpler ways, and it turns out that the symbolic regressor can't really recover the equation at all. And then you have to tinker with these sort of different parameters of the algorithm to hopefully try and get it to converge. But having said, even with the limitations, symbolic regression, in closing is a really interesting tool. I think it'll only get better over time as there's more research. The algorithms, the functions get better in Python, and it's really exciting because you can have a bunch of data, and you can get sort of a functional relationship that is not dependent upon some assumption, like an assumption of linearity, or an assumption that the function is exponential, or any kind of assumptions. You just kind of pass through the data and let and your features, so x naught, x1, x3, however many, in our example we have sort of x naught and x1 only, so we can imagine the solution surface in 3 dimensions. But you can have more than that, and then you can't even sort of plot it, so to really understand what might be going on. But through this something like symbolic regression, you can recover some sort of functional form, and also recover how well it performs against some other methods that don't produce this sort of beautiful closed form equation, like decision tree or random forest or neural networks. They're like complicated methods that don't produce these closed form solutions. But with symbolic regressor, maybe you can produce it, and if it performs better than the other ones, why wouldn't you use that? You have all of a sudden gained far more insight into the dynamical system that's generating the data, versus using some technique like neural networks that can be very useful, but it offers limited insight into the relationship and the governing equations generating the data. So hopefully you like this video. It's about symbolic regression, and hopefully you add it to your toolkit. Till next time, thank you for listening.